Guys, I hope the screen is visible to all of you.
Yes, Rajiv.
Just
Yeah,
in,
good.
oh yeah, great,
Go ahead.
thank you. Hi guys, we'll be kicking off this session with the introduction to SD-WAN Fabric, uh, where I'll have one of my peers, Akama, will be helping me delivering this session. We both work in the SD-WAN tag team, and it's been almost 2.5 years. She's very much more experienced than me, so she'll be helping along uh, 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 all of us with this session. So let's jump into it. Um, so this is the section agenda, the kind of overview what we'll be checking today. We'll try to understand what is SD-WAN. Following with the SD-WAN overview, we'll discuss what are the different important planes or the part of architecture in the SD-WAN. As you can see here, the orchestration, management, control, data plane. We'll try to understand what this each section or this plane is, what its job, what it's consists of, and how it works. Follow up with the commonly used SD-WAN fabric terminology, which you will be which you have to get used to work in the SD-WAN domain. We'll also try to understand how the fabric operates. What are the different key things the fabric or the SD-WAN must perform for a successful fabric operations, and then when quickly look into some of the options available to us in the Cisco SD-WAN deployments. Okay, so let's quickly get into what is SD-WAN. This is something not happened. I mean, something. This is something which happened around the 2019, where the Gartner gave us some uh, definitions about what can be the SD-WAN, which would have your branch router and the CPF functionality. It should be able to operate autonomously during loss of connection to the controller. Then you would have full support of hub, spoke, partial or full mesh, so on and so forth. And the zero touch ZTP, zero touch configuration, it should provide security. It should provide seamless delivery depending upon, irrespective of the location of where the users are, and also where the applications are, and of course the dynamic traffic steering. So the list keeps on increasing. And if we just summarize it into the basics of the SD-WAN capability, it can be defined in points like, it should be able to perform the circuit load balancing. It should be able to handle the direct internet access, which means that if my user is close to, let's say, an SaaS application like Outlook, it doesn't need to go to a remote location and then break out. So the user should be able to directly reach that SaaS application. It should be able to provide a centralized management and orchestration. You should be able to deploy any site anywhere in the world, sitting at the one of the one at one location. And of course, it should result in some kind of uh, uh, cost saving in terms of business. So it should be able to lower our circuit costs. So how all these capabilities are clubbed with the some of the extended capabilities which are offered by the Cisco SD-WAN solution. It provides a multi-layer. It provides the protection of multi-layered security with the help of security and segmentation, and kind of the analytics and the visibility it provides with the help of analytics tool. We perform the application optimization with the help of application-aware routing. We'll see in the upcoming slides and upcoming sessions how it is done, how we perform voice optimization, SaaS, IaaS optimization, and of course the app-aware dynamic routing. And at the scale, of course, as the enterprises grow, we have many large scale deployment which is successfully running. So we'll see how we are open and programmable, and how we can MSPs can leverage the multi-tenant and multi-domain options using the Cisco SD-WAN capabilities. Before we start that, let's also try to understand what kind of transformation the network has to go through, depending on the requests which are keep coming in as our work environment and the location of the applications and the users are changing. So our network earlier used to be the hardware centric. We have to the businesses were so keen on the hardware part. Like if we bring up, if we have to bring up one location, these are the number of hardwares which needs to be shipped at that location, and then the extra, the cost, time factor which was associated with it. But these days, everything needs to be software driven. I mean, it's not that we have to fix on just one piece of hardware. That could be anything, and it should be it should be available on the fly. The most common example is the NVFs, I'm sorry, which we can add to any given branch location and spin up any component, network component. Earlier, everything, as I mentioned, was manual, that businesses have to schedule and site appointment to bring everything up. But now, if we want to introduce a new service, it needs to be automated. I can, with the help of Cisco SD-WAN, I can bring up, let's say, a firewall service anywhere in my network, and accordingly, my traffic can be routed. Only the interesting traffic can go through it. Probably we'll see some of it in session. The access to this network was like primarily closed, that only few guys would have access to it. But here, when I say access, I mean who are able to work on it. But these days, it has to be programmable. Your network has to see what your business needs, and accordingly, it needs to program itself. And we'll see. One of the options would be one of the examples I can use, the AR, and we'll see how it can change the traffic pattern on the fly when there is congestion in the network. So earlier, our approach was more reactive. Like if something happened, then we have to do this. But here, we need to be predictive with the help of the tools available to us, like analytics, and the amount of the stats and data available to us in the vManage. We can proactively look into the data, the historical data, and figure out what is actually needed in a given time. Maybe let's say the shutdown, or some broadcast is coming, and how we can manage our resources, so we can be predictive in that. And of course, we always historically followed the network intent, what network is doing. But here, we need to understand what business is doing, and accordingly we have to our network should work. So few things to remember before I hand this over to Akama. That these are the few things. If you see this icon on the left, it's basically a V-Edge router, and more recently, we are moving into more and more C-Edge architecture. So this is a C-Edge, which is basically an SD-WAN router, a data plane component. The VSmart controller, the vBond orchestrator, and of course, you will be spending a lot of time with the last icon, the vManage, which is the management application. So with that, I'll hand this over to Kama now, and she'll be able to drive this. Kama?
Oh, hello, Rajiv. Thank you.
I'll run the slides, it's fine.
Yeah. Could you move on to the next slide, Rajiv? Yeah. Hello, everyone. So thank you, Rajiv, for giving us an insight into why we need SD-WAN and how is it different from the traditional networking. So moving on, let's understand how the SD-WAN solution looks like, overview. So as we all know by now that it uses the principles of software-defined networking. So in software-defined networking, we classify a fabric, or we divide the fabric into 4 main planes, which is the orchestrator plane, management plane, control plane, and data plane. So in a Cisco SD-WAN, the orchestrator plane is taken care by the vBond. So vBond is a node responsible for orchestrating the fabric and ensuring the right components get added to the fabric. So any device or node, if it has to join the SD-WAN fabric, it has to authenticate to the vBond first, and then it can go through rest of the operations. We will discuss more about these planes in our upcoming slides. With the management plane here, we are referring to the node, which is the vManage. vManage is mainly used for monitoring and managing the overlay in a very centralized fashion. So it also makes use of API queries, which we will discuss again in our upcoming slides. Then we have the centralized control plane, which is also called the brain, which is taken care by the VSmart. So one of the main concepts that we use in software-defined networking is we remove the control plane operation from the end routers, and we use a separate node for that, which is the VSmart here. So the VSmart takes care of all control plane operations required for the fabric to function. And then we have data plane where we have edge routers, which can be either a physical form router or a virtual router, which will form control connections with all the 3 controllers, vBond, vManage, and vSmart. Upon successful control connection with these 3 components, we will learn the TLOC information, which we will discuss more in our upcoming slide, and thereby we form the IPsec data tunnels between the routers through which the traffic is transmitted across the sites. So let's discuss in detail about these components in our next slide. So moving into the orchestrator plane, which is the vBond. So it orchestrates both control and management plane. So on any node that we add to the overlay, we configure the information of the vBond. It can be a host name or the IP address of the vBond. So it acts like a first point of authentication, be it a vManage when you spin up a vManage or a vSmart. It has to first connect to the vBond successfully. Only after that, it can talk to other nodes in the overlay. So vBond is a first point of authentication, and we use a whitelist model, which we will again discuss in our upcoming slide, how we use that. And then vBond also takes care of distributing the vSmart and vManage information to the edge routers. So as I said, on any node, we configure only the vBond IP or host name. The routers do not have any information related to vManage or vSmart. We do not configure it. So when the router contacts the vBond and successfully authenticates to the vBond, it's the responsibility of the vBond to share the vManage and vSmart information with the router. Once router receives the vManage vSmart information, only after that a router can attempt to form control connection with vSmart and vManage. So that is one of the responsibility of the vBond. The other important responsibility is it facilitates NAT traversal. Let's say any node in the overlay, be it the edge routers or the controller, if it is behind a NAT device, it's the vBond who learns that the device is behind a NAT device, and it learns the public and private IP for the node and shares it with other controllers. And again, vBond is a highly resilient component. Next, let's moving on to the management plane, where we discuss about vManage, which I feel is heavily used by all of us while working on SD-WAN. It's a single pane of glass for day 0, day 1, and day 2 operations. So from the time we decide to onboard a router till the life cycle of a router, we can manage it using the vManage. So we use a concept of zero-touch provisioning where very less manual intervention is needed to onboard a SD-WAN router. During that process as well, in the vManage, we can map a configuration template, and vManage takes care of pushing the complete configuration to the router and enable the router to form control connection. That way we take care of day 0 operation as well. Once the router is onboarded with basic configurations, later if we have to tweak any configurations on it or add or remove any configurations, you can do it easily with the vManage. With the vManage, we can also deploy it in a multi-tenant mode, meaning let's say in an MSP environment where we have to manage multiple customers, we can install multi-tenant vManage where we can manage multiple customer overlays using one GUI. We can switch between multiple vManages of various customers and manage it easily. vManage also enables centralized provisioning where we can push templates to multiple routers at the same time. Let's say we have to roll out a specific change quickly to multiple routers, we can perform that using vManage. Also, we can configure policies like centralized policies or localized policies, app-aware routing policies, easily using vManage with the help of Wizard and GUIs. One of the core functionality of vManage is troubleshooting and monitoring. With monitoring, vManage periodically collects the statistics information from the edge routers as well as other controllers and displays it at the UI. So we can quickly refer to the vManage statistics and understand how the overlay is performing. Also, we have the option to run real-time commands on the routers to fetch the outputs quickly using the GUI. We also have various troubleshooting tools like speed tests, packet captures, traceroute tools, which can help us with troubleshooting network-related issues. The other advantage or benefit of vManage is we can perform software upgrades. Else, there is no need for us to log into each CLI of each router and manually upgrade each of them. Instead, we can upgrade multiple routers in a single shot using vManage. Also, we have role-based access controls to the vManage UI where we can decide which user can perform what actions on the vManage UI using our role-based access control. One important advantage of vManage is we have programmatic interfaces where we can poll the vManage using API queries. Let's say we have a monitoring system in our environment and we would like to fetch SD-WAN related statistics. We can poll the vManage using REST APIs and fetch those information and display it in our internal monitoring tools. Again, vManage is a highly resilient node. Moving on with the VSmart, which is the control plane for our SD-WAN Fabric. One of the important role of VSmart is it should be able to push the TLOC updates. When I say TLOC updates, for the edge routers to form the data tunnels or the IPsec tunnels, the VSmart is the one who have to share the information, the private IP, the public IP, or the private port, public port, along with this additional information of remote routers to this local router so that this router can form BFT or IPsec tunnels with the other site routers. Thereby, it facilitates the fabric discovery. Also, it helps in VSmart is the one who advertises the routing information of different sites. Thereby, the routers can route the data traffic. The VSmart disseminates the control plane information between the VHUs. In SD-WAN, no control plane information can be shared directly between the routers. The control plane information is always shared with the VSmart, and the VSmart takes the responsibility of advertising it to other sites. Thereby, the VSmart, the router will not participate in any control plane operations. It implements the control plane policies such as, let's say, we do not want a full mesh overlay. We do not want all the routers to be able to form BFT sessions with all the other routers. Instead, we have few data centers. Only to that, if we need the branch size to talk to, we can implement hub and spoke policies. So if we have to tweak the way the overlay comes up, or if we have to tweak the way the routing information is advertised to the sites, we can build control policies, and these policies are installed, or it'll work on the VSmart operation. So VSmart compiles the control policy and implements so that it takes action on the TLOC or route advertisement. Also, it takes care of distributing the data plane and app route policy, where if we have a centralized data policy, let's say for QoS, the VSmart, it is configured on the VSmart. VSmart compiles a policy, and then it is pushed to the end routers. Once the edge routers learn these policies, it will be acted on the data traffic. And with all this in place, we drastically reduce the control plane complexity. And this is a highly resilient node. Moving on to the data plane, which is our edge routers. It can be a Viptela router or a Cisco-based router, which we also refer as CH. In SD-WAN terms, it is called edge router. Now, between these routers, we have a secure data plane tunnel, which is our IPsec. So the IP, once we learn the TLOC information or of other routers, the routers will form the IPsec tunnels between themselves. Within the IPsec tunnels, we send BFT packets to check the liveliness of the tunnel. So thereby we ensure that the traffic, the user traffic, is transmitted through a secure channel. The routers establish, so as we all know by now, that routers form control connections with VBON, vManage, and VSmart. Once we form successful control connection with the VSmarts, the routers establish a OMP peering with the VSmart. Now, with the help of this OMP peering, through this OMP peering, we transmit the routing information as well as the TLOC information. So it is important for us to have a OMP peering between the router and the VSmarts for us to receive the control plane info, for the routers to receive the control plane information. As I mentioned earlier, the data policies and the app route policy, which are configured on the VSmart compiles it and pushes it to the routers. Now it's the router who implements the policy, and it will be applied on the data traffic. The routers also have to periodically update the statistics information to the vManage. So the vManage establishes a netconf session to the routers, and through the netconf sessions, the statistics are exported to the vManage. We also leverage traditional routing protocols on these routers, on the edge routers. We can configure OSPF, BGP, VRRP. On CHs, we can also implement EIGRP on the service side or on the transport side VPNs. These routers do support zero-touch provisioning, where very less manual intervention is needed to onboard a SD-WAN router at a given site. And as I mentioned earlier, it can be we support physical form of routers as well as virtual form of routers. So now that we understand different planes better, this is how the complete SD-WAN fabric looks like. So we have three controllers: vManage, vBond, VSmart. We establish control connection among themselves. So the control connection between the vManage, vBond, and VSmart should be intact. So once we have the control connection successfully up between the controllers, the routers will talk to the vBond first. It'll establish a DTLS tunnel with the vBond first, and then the vBond will share the information of vManage and the vSmart with the routers. Once routers receive that, routers will establish DTLS tunnel with the vManage and the vSmart. Once we successfully form control connection with the vManage and the vSmart, the routers will tear down the connection with the vBond. But periodically, we attempt to form the connection with the vBond just to check if we can successfully talk to the vBond. The minute we are not able to form the connection successfully with the vBond, we will tear down the connection with other controllers as well. So it is very important for us to be able to successfully form the connection with the vBond at any given time. So once the routers have formed successful control connection with the vManage and vSmart controllers, it will learn the TLOC information from the vSmart of other routers. With that information, we form the data plane tunnels between. So the data plane tunnels or the IPsec tunnel is formed between the routers. So this is how the complete SD-WAN fabric looks like. All right, moving on. So while we discussed about vBond, I mentioned about a whitelisting model. So how do the controllers or the vBond validate that the connection that we are receiving from the router is from a valid router, and it has to allow the connection to go through? So we use something called whitelisting model, where we have a plug and play portal where all the serial numbers are updated. So we download the serial list from the PNP portal and upload it to the vManage. So that will take care of whitelisting the routers. Now, coming to the controllers, the first component that we bring up in while spinning up SD-WAN overlay is the vManage. So once the vManage is up we mention the vBond IP address details. We bring up the vBond, we specify the vBond details. And then when we spin up the vSmart, now in the vManage, we have to add the vSmart and vBond using the IP address. Once the vSmart and the vBond is added successfully, the vManage will talk to the vSmart and the vBond, and it will learn the serial numbers of vSmart and vBonds. So now the vManage has the serial number of all the control plane components. With this, what vManage does is once it learns all the serial numbers, this list, which is also called as vSmart list, will be pushed to both vSmarts and vBonds, so that all the three components know the serial numbers of the controllers, SD-WAN controllers. So all the three components know the serial numbers of the valid controllers. Post this, we attempt to form the control connection. So vManage will first talk to the vBond. vManage has the IP address information of the vBond. It will start talking to it'll attempt to form the DTLS tunnel. Now, when we attempt to form the DTLS tunnel, when we refer to DTLS, it is TLS over UDP. So TLS is nothing but we need to perform a TLS handshake for the TLS connection to come up. when we refer to TLS handshake, certificates come into picture. So this is one of the important parameters that we need to take care of while bringing up the control plane. So we need to ensure that all the three components have valid certificates installed. Now, coming to the topic of certificates, there are three ways or three options available for us. One is the semantic certificate, second, Cisco certificate, the third is the enterprise CA. So talking about semantic certificate, by default, all the controllers, even the routers, SD-WAN routers, have semantic root certificate installed on them. It comes as a part of the software. Now, let's say we decide to use semantic certificate. We already have the root certificate involved. vManage, using the vManage automated process, the vManage can generate the CSR from the vBonds in the VSmart, export it to the semantic certificate authority, get the certificate signed, and install the semantic certificate on all the controllers. With this, during the TLS handshake, when the certificate is exchanged, the controllers can successfully authenticate each other, and the DTLS or control connection can come up. So one point to be noted is when vManage generates the CSR, gets the certificate signed, vManage learns the serial number, certificate serial number of VSmarts and vBond, and in turn it is pushed to VSmarts and vBond. So anytime we receive a DTLS request with a valid certificate serial number, which is already present in the valid VSmart list, we should be able to get the connection go through. Along with the certificate serial number, we will also ensure if the certificate has the correct org ID configured, organization name, which is again part of the certificate that is exchanged. So this is about semantic. Now, even with Cisco PKI, all the controllers have Cisco root certificates installed on them. So we can generate the CSR, get the certificate signed. We can use our PNP portal to quickly get the Cisco CSR signed with Cisco CA. We can install the Cisco certificate, and that will also help us bring the control connection successfully. And third one, if our organization have an enterprise certificate authority, and if you would like to use that, we can use enterprise certificate authority as well. One thing here is to take care of is we need to ensure that the root certificate of our enterprise CA is installed on all the nodes, controllers, as well as on the routers. Once we have the root certificate installed successfully, we can generate the CSR from the controllers manually and get the certificate signed and install the signed certificate on the controllers. So this is how we can install this certificate on the controllers. Now, moving on how we whitelist the routers, the same procedure applies for the CAs as well. So in the previous slide, I mentioned that in the PNP portal, we can upload we can update the serial number information of all the routers that will be part of the SD-WAN Fabric. So once the serial numbers are updated in the PNP portal, we can directly sync it to the vManage. We have an option to quickly sync with the smart account. We can use that. As we can download the serial list from the PNP portal and import it, upload it to the vManage. Now, once the vManage has the list of valid serial numbers, the vManage will push it to VSmart and vBond. So the steps I explained earlier, where we will do a check on the serial number as well as on the org name. Also, there will be a challenge imposed by the controller, which is again part of the authentication process. These steps are carried out at each controller, not just for vBond. These checks will be done on vManage as well as on VSmart. So it is important for all the three controllers to have the valid VH list. And it is a responsibility of the vManage to push the valid router list to both VSmart and the vBond. So there are three modes in which we can set the routers in. So once we push the serial numbers to these controllers, let's say we are not onboarding a specific router anytime soon. So we can set the router in staging mode. So which means you can prepare a configuration template for it. We can attach it to the serial number and we can leave the router in staging mode. And the time when we onboard the router, we can move it to valid. So the status valid indicates that anytime we get a request from that specific serial number, we are ready to form the DTLS tunnel. So that is what valid means. Invalid is we will no longer accept the control connection request coming from that serial number. Am I audible?
Yes, Akama, you're audible.
Okay, cool.
Yes, you are.
Thank you. So one of the scenario where we make use of invalid state is, let's say we have already replaced a router and we are no longer using that serial number in the fabric. We can mark it as invalid so that we don't accept any invalid connection. I think we'll have to give a minute to Rajiv to switch the slides. Sorry, folks, just allow me a minute or two. Let me check with Rajiv if can.
Hey, Akama, looks like Rajiv has some problem with the WebEx. So do you want to take the ball and share it?
Yeah, I can do that, Guru. Yeah, could
Okay.
you?
I'll move the presenter to you. Yeah.
Sure. Okay, let me share my screen.
Akama, my WebEx got crashed. Give me a second. I'll join back. Okay.
Okay, sure.
Pass the host control to you. Can you try sharing?
Sure, Maria. I'm trying to share my screen, but there seems to be some issue here to share my screen.
Any issues, Akama?
Yeah, I'm not able to share my screen because it says some preference issue. I tried fixing it on my PC, still I'm not able to share it.
Yeah, I joined back. Don't know what happened. Apologies, guys. Looks like the issue did happen. Guru, if you pass the ball, I'll try.
I'll sure pass it on Rajiv.
Yeah, thank you, Maria.
Yep, I've done that.
Okay, just give me a minute. I hope it's visible now.
Yes, Rajiv. We
Yeah.
can see.
Sure. Thank
Yes,
you, Maria.
Rajiv. Thank you. Can you move a little ahead, Rajiv? One step ahead. All right, thank you. Okay. Sorry about that, folks. Moving on, so we understood how we learn the VH serial list and what are the different modes we can set it to. Now, coming to the certificate part for the routers. So by default, the VH hardware routers have a chip which is called TPM chip, tamper-proof chip, where we already have an AVNet certificate stored. Now we can opt to use that certificate for the control connection, and our controllers, the VBond, VSmart, and VManage, already have the AVNet root certificate with them. So the VH routers can can advertise the AVNet certificate during the TLS handshake, and with that also the DTLS tunnel can come up. Now, if we would prefer to use semantic certificate for routers as well, again, as I mentioned earlier, the semantic root certificate is already present on the routers. We can generate the CSR for the hardware routers. We can get it signed from semantic and install it on the routers. Thereby, we use semantic certificates for control connection. We can also use Cisco certificates for routers as well as the controllers. Again, we already have the Cisco root certificate installed as part of software. We have to generate the CSRs and get it signed. Again, as I mentioned earlier, if we decide to use Enterprise Certificate Authority, then we will have to install the root certificate of Enterprise CA on both the routers and the controllers. And once we have the signed certificate installed, the control connection should be able to come up. So this is specific for hardware routers. When it comes to software routers or the cloud-based routers, the process is slightly different. Again, when we add the routers in the PNP portal, we can also add the cloud routers. So when we add the cloud routers, and we can pick a number based on the number of cloud routers that we would like to have in our overlay. We can create those many serial numbers in the PNP portal, but there it will generate a UUID for each of the cloud routers. Once that is imported to the, once that is uploaded to the vManage, we can generate the bootstrap config for each VH Cloud router, and in the bootstrap config we will receive a UUID and a OTP. It's nothing but a token. Using the UUID and the OTP, we activate the cloud router on the CLI of the router. So once the cloud router is activated, we can generate the CSR depending on based on the CA that we have chosen. We can generate the CSR, get this CSR signed and install the certificate. But we need to remember that we'll have to ensure that the root certificate of the corresponding CA is installed on the router. Again, Cisco root certificate and semantic root certificate is already present as a part of software. The root certificate should be taken care for enterprise CAs only. Now, once the VH Cloud has a valid certificate installed, it will talk to the controllers. Again, as the same process that we have that we followed for hardware routers, right? And then the DTLS or the control connection comes up. One aspect with the control connection is we need to ensure that all the components, controllers and routers have the root certificate installed for the CA that we have chosen for our overlay. So that's how we whitelist the VH Cloud routers. All right, moving on. Rajiv, can we move on to the next slide? Yeah. So from here, we will discuss about how zero-touch provisioning works. Rajiv will take over from me and explain us how ZTP works.
Okay, thank you, Kama. Thank you very much for giving us this overview session about the different planes and what are they used and everything. So now we jump into the plug and play, the PNP Vedge secure bring up zero trust, the process widely referred as ZTP, zero touch provisioning. So we as we have already discussed about the different components, the vBond, vManage, and VSmart. Along with that, there is a ZTP server, which is the zero-touch provisioning server. This already has information about the VH serial list and the VH serial list, which is gets synced from the PNP account. An administrator needs to perform all these operations. Of course, adding we have to add the whitelist so that it can be sent to the controllers along with the identity trust. What we want this device to be, which we are trying to onboard, whether it is whether it's invalid staging or the active mode. With respect to the control connections, and of course, if there any configuration template is assigned to it, all this information is present in the vManage. So that's how it goes. So once this device is shipped on, let's say, one of the branch locations, it's powered on. It gets IP via DHCP, and it is able to resolve a URL which is ztp.cisco.com. I think now it's cisco.ztp.com. It gets resolved. It presents the information it already has with the serial and the UID. It gets redirected to its corporate vBond, and then the regular onboarding or the authentication and authorization process follows, and that's how we onboard this device. So maybe we can discuss this in a little more detail, what all these steps are involved one by one. while we onboard this Vedge appliance. So again, here we are assuming that at the branch location, we have the IP address is available via DHCP, and it is able to access internet, and DNS is able to resolve the ztp.webtela.com. So once the device, excuse me, powers up, it sends that I have internet access. It sends its query to ztp.webtela.com. After looking at the serial number of this Vedge, the ZTP server knows that to which organization, excuse me, it belongs, and then it redirects it to its corporate vBond, or the orchestrating plane. And then the initial communication goes out to the corporate orchestrator, and we receive the initial configuration from the vManage. And once it gets the required minimal config from the vManage, we'll see in the upcoming slides, it will do a full registration and the configuration to all the controllers. And yeah, so that's how your zero touch provisioning, ZTP, works in contrast to the Vedge appliance. Let's see how this ZTP process is different when it comes to the Vedge Cloud. Akama already briefed us about what are the components required to onboard Vedge Cloud. We generate a cloud init config. It looks something we see in this blue section here. It would have an OTP, which is a token. It will be an IP address of the vBond, which is the orchestrator plane orchestration, along with the UID and the org name. So once this cloud config is used as a cloud init while booting up a Vedge Cloud, when we are deploying the VM, looking into this information, because as we know, we have to we need to ensure that there is a reachability to the vBond, and using these parameters, when this Vedge Cloud reaches to the for the initial with the initial control connection communication to the controllers, it gets the initial device config from the vManage, and once that config is loaded, it gets a full registration and configuration from the vManage. So it's sparsely different how we onboard Vedge hardware versus Vedge Cloud. Now, some of the Viptela Fabric terminology, which we should all be aware of, because it's something which we will be using day in, day out while working on the Cisco SD-WAN Fabric. OMP, this is the Overlay Management Protocol. This is basically the control plane protocol, which distributes the T-lock information. You've been hearing T-lock a lot, so we'll discuss what is T-lock in the upcoming slides. The reachability, security, and the policies throughout the fabric. T-lock, transport locator, which is basically, as the name implies, gives us the information about where a given endpoint is present, the transport locator. It also has the next hop route attributes, which we'll be discussing. Color, this is very unique to the SD-WAN environment, where we can color our different interfaces, depending on what kind of topology we want to achieve. Let's say we have two sites and they have two colors. So there are different colors. One is MPLS, other is Biz Internet. So we can choose whether there should be a full mesh connectivity or it can be restrict on the basis of colors. Site ID is a unique per site numeric identifier. We can say something like like a router identifier when it comes to BGP or when it comes to BGP. I'm sorry, that's system IP actually. A site ID is uh, when we deploy, let's say a VEdge, either the hardware component or the software component, we specify a site ID, which can help us denote what is the location, and it can further be used while applying, let's say, a policy that if we want to apply, uh, let's say, a given QoS policy to some specific sites, so that can also be used. System IP, I mistakenly explained that it is the unique per device and IPv4 notation identifier, which is also same as the router ID, which we use in BGP and OSPF. Org name is another important terminology which we used in case of SD-WAN, which defines your the overlay. So once the organization name is, let's say, configured on a box, it can only talk to the devices which belongs to that org name, that given org name. If you want to move it to some other, then you have to change the org name. So org name would be, you can say, one of the things which should match in a given SD-WAN fabric so that all the devices can talk to each other. There are certain other factors like cert and everything, but org name is one of the important factors. And of course, the VPN, which provides the device level and network level segmentation. We see that we only allow the devices within the same VPN to talk to each other. So we need to ensure that that also matches. So that's how our Cisco SD-WAN topology looks like. It's kind of a general topology, and we see how that terminology is associated when we brief on this SD-WAN topology. So this will be our site ID. So my R1, R21, and R22, they both belong to site 2. So let's say if any policy is applied to site 2, it will be applied to both these routers. It will not look into any other SD-WAN terminology or SD-WAN component like the color or the router ID or anything. If something is applied to site 2, it will be applied to all the devices which are present in site 2. And there can be more devices, maybe some other location as well that can we can also configure the same site ID, and that policy will be applied to that device as well. System IP, we already discussed. It's kind of an IPv4 device, an IPv4 notation device identifier. It's unique per device. So multiple devices can be part of a single site, but yeah, system IP will be unique per device. And these and these individual, let's say at this given point, links will become TLOC, but they will comprise of with the information of system IP, color, and encapsulation. So a TLOC, when we say a TLOC, is basically three things. It carries the system IP of the device. It carries the color of that given link. Here we use two colors, MPLS and the internet. And then the encapsulation. We have two types of encapsulation, IPsec, which is the on by default, But if we want to turn off the IPsec, we can also use GRE. So OMP, the Overlay Management Protocol, distributes these OMP, these TLOCs, this TLOC information, like where this transport locator is located in the given SD-WAN fabric. And within that TLOC, we would receive the system IP of the device, what is the color on the given specific link, and what kind of encapsulation. This is exchange, and after this exchange, our overlay brings up, depending on, we have the reachability between the two TLOCs. Of course, the color. Each tunnel interface is assigned a color, which is shared within the TLOC. So let's see how our fabric operation looks like. Depending on here, I mean, here we are assuming that these two devices, they have already authenticated to the orchestration plane or the vBond. They know what are the different controllers available, and these are the two separate individual TLOCs they have: T1, T2 on VH1, and T3, T4 on the VH2. So we know that there are two transports. They would definitely have, at this point of time, we know there would be a system IP assigned to these VHs. There would be encapsulation, and of course the color on these T1, T2, T3, and T4. So let's see how it works. So first, it will bring up the DTLS or TLS tunnel to set up the control connection with the VSmart. So once my OMP session is established, the VSmart will send the remote TLOC information to these two VHs. So VH1 would receive the TLOC information from VH2 as T3, T4, and on the VH2 we would receive respectively T1 and T2 coming from VH1. Once this information is received, depending on the reachability, we would then set up our tunnels between these two locations. This will be the IPsec tunnels. Akama also mentioned about the BFD. It is used to detect the liveliness of the tunnel, and along with that, it is also used to monitor certain other aspects. Three primarily: the link latency, jitter, jitter, and loss, which these three factors can be later used while deploying application-aware routing policy, which in further can be used to further steer the traffic. Please don't get bogged down. All these things will be covered in detail when we do some data plane and data plane slides. These will be discussed further upon. I'm trying to give you the information as much as I can. How we while within this fabric walkthrough. And of course, this BFD then runs on these IPsec tunnel. Now, BFD is statically turned on. We cannot turn off BFD because it gives the liveliness of these transport or IPsec tunnels, and we cannot turn it off. Now, let's say we have some connected subnets in VPN1 on the both sides. That subnet A and subnet C. Once these tunnels are set up, BFD is up and running. These routes will also be exchanged between these, and there will be an periodic OMP update, which gives us the information about reachability, security, and policy. Reachability, we already discussed in terms of along with TLOC, we get IP subnets, which are present on the respective VH1 and VH2. And of course, since there is an IPsec tunnel between these two locations, so there will be encryption keys, and there will be the rotation of the encryption keys, which depends on what is the timer set for that, and of course the centralized policy data and the app route policies, which we get from which VSmart gets from the vManage, and in turn sends it out on the VH devices in the OMP update. Yep, between these two locations, along with the policies. Okay, so now we'll quickly jump into the deployment modes. What are the various deployment modes which are available to us, and how we can leverage these modes depending on what we want to achieve and what our business allows. And for this section, I'll hand this back over to Akama. So, Akama, over to you.
Thank you, Rajiv. Thank you for explaining ZTP and Fabric operation for us. All right, so let's look into the various deployment options we have. So when we talk about deployment options, it's primarily for the controllers because the edge routers will be installed at the site itself. So when it comes to the controller deployment, we have three options. One, it can be hosted on the Cisco Cloud, where we take care of assigning the required resources to the controllers. So the vManage, VSmart, and vBonds can be hosted in the Cisco Cloud, and we will alert the customers if there is any sort of like high memory usage or high CPU utilization that's seen on the controllers. So we basically look into the operations, but the configurations, pushing the templates, these things will be taken care by the customers depending on their need. The resource allocation and monitoring the controllers will be taken care by the Cisco Cloud Ops team. We also have, we also can deploy the controllers in the MSP clouds. So if we have a private cloud and owned by MSPs, we can choose to deploy the controllers in the MSP clouds as well. And then we can also deploy the controllers on-prem using either we can deploy it on the hypervisors that we have, ESXi or Microsoft Hyper-V hypervisors. So since the controllers are all virtual instances, we can choose to deploy it on premises as well. All right, these are the three options we have. So the next slide is about the solution scale. Let's say we expand the SD-WAN Fabric, we add more and more sites to the SD-WAN Fabric. A need might arise to increase the number of controllers we have, the vBonds, vManage, and the vSmarts. So based on the number of routers we have in the site, we can opt to use more than one vBond so that the load is shared among the two vBonds rather than overwhelming one vBond with a lot of requests. Similarly, we can also opt to use vManage in a cluster where we can have 3, 6, or 9 vManage depending on the size of the overlay in a cluster, where the control connections are distributed among the vManage. Each vManage node will form control connection with a set of routers. Also, we can distribute the statistics information, so that not a single vManage need not get overwhelmed by handling all the statistics information it receives from the complete overlay, from all the routers on the overlay. So the statistics information can be distributed as well, thereby it helps in load sharing. Similarly, for the VSmart as well, we can have more than one VSmart, wherein it will help push the OMP updates. We can load balance the updates that are advertised from the VSmart to the routers. We can also configure groups where a set of router can form control connection with specific vSmarts only, thereby again a single vSmart doesn't get overwhelmed. At a given site, when it comes to routers as well, we can plan, we can design so that we have more than one router installed at a given site. Again, we can choose the platform that we need based on the IPsec or the BFT tunnels that each router have to handle. Depending on that, we can add more routers or controllers to our fabric. Talking more about the redundancy with regards to VSmart. So even if we have more than one VSmart in our fabric, the VSmart themselves will have OMP peering with each other. With the OMP peering, they ensure that the routing information as well as the TLOC information that each VSmart have are in sync. So anytime one VSmart goes down, the other VSmart can quickly take over so that there is no impact on the user traffic. At max, we can have 3 VSmart controllers. VH can form control connection with 3 VSmart controllers for redundancy purpose. And as I mentioned, if one VSmart goes down, the other VSmart controllers can handle the updates coming from the routers. Also, we have something called graceful restart. Let's say the routers lose, let's say we have 2 VSmart controllers in our SD-WAN fabric, and router has control connection with both the VSmart, but maybe due to some underlay issue or some issue, we lost control connection with both the VSmarts. In that case, our data plane can stay up for a certain time, which is decided by the graceful restart timer. By default, we set it to 12 hours, but it can be increased up to 7 days. So let's say we have set it to 12 hours. So from the time we have lost control connection to the VSmarts, both the VSmarts, the BFT tunnels can stay up till 12 hours before we bring it down. But during these 12 hours, there will be no fresh routing updates or TLOC updates that will be received by the routers. So that's about the VSmart redundancy. Moving on to the vManage redundancy, as I mentioned, we can use, based on the number of routers we have in the overlay, we can opt to use vManage cluster. It depends on the size of the overlay. We can choose to have 3-node cluster or a 6-node cluster or a 9-node cluster, and we can distribute the NMS services. We can choose to enable certain services on one node and rest of the services on the other nodes. So thereby we can load share the jobs that the vManage has to carry out among different nodes. And in the cluster mode, again, let's say we have 50 routers in our overlay. Around 20 routers will talk to vManage 1, rest 15 might talk to vManage 2. And so thereby we ensure that the control connections are also equally distributed among the vManage nodes. even with vManage, we ensure that the redundancy is completely intact. The information, the config information is in sync between the vManage nodes. In a scenario where we have a data center and a DR setup, we can choose to have 2 cluster and ensure that the configuration database of the vManage at the DC side is imported to the DR side. Thereby, we can ensure that if the DC side goes down quickly, we can fall over to DR. And in case of the vManage servers go down, there will be no impact on the fabric operations or the data traffic, as long as the routers have control connection with the VSmart intact. The only two options that only 2 areas that will be impacted if the vManage goes down is the statistics will no longer be collected for that time duration. Also, we will not be able to monitor the overlay health during the time when the vManage is down. So once we have the complete SD-WAN fabric up from the data plane perspective, this is how it looks like. Each router at a site can have more than one transport, public transport like internet circuit, and a private transport like an MPLS circuit. So with this, we can we establish BFD sessions as we discussed earlier, and with this, through the overlay, we can access the resources at our data centers. We will have again SD-WAN routers to which we will have BFD tunnels established to. Through the tunnels, we can contact the servers at our data centers. Also, we can, if we have a private cloud sites, we can talk to those sites as well through the SD-WAN Fabric. And then if we have services hosted in virtual private clouds like Microsoft Azure or Amazon Web Services, we can deploy cloud routers there and access the resources hosted in the private cloud in the VPCs. Also, if we make use of SaaS applications in our organization, we can connect to those applications using. We also have the features of Cloud OnRamp, where we can securely talk to these applications and users can access these applications. So this is how the complete SD-WAN deployment looks like. So this brings us to the end of the session of the overview to the SD-WAN. I hope this session was useful to understand SD-WAN.
Thank you, Akama and Rajiv. Yeah, we can take a 15 minutes break and we'll come back at 10:45 a.m. India time. welcome back, everyone. Afroz, probably you can start with the products.
Yeah.
You're the presenter now.
Yeah. Is anyone sharing this slide screen?
No,
For the product?
maybe you can share it yourself, Afroz. Yeah.
Okay. Just give me a second. So I'll just give a brief on what we have today on the product lines, and you'll probably see this in the screen. So basically, when we look at the enterprise routing pin, right, you'll have 3 or 4 product lines that would come out, right? The ASR1K family, which is the oldest of the family, it goes all the way back to 2007. Then the next gen ISR4K family, the ISR1K family, and then also you also have the Viptela family, or now also the Nutella family, which would be the next gen, right? So if you look at the ASR1K family alone, there are multiple flavors, and you break it down into 2 parts, right? One is your fixed chassis and one is your modular chassis. So if you look at the first 5, which you have, the 1004, 1006, 13, 6X and 9X, they come from the modular chassis. Now, how they differ from each other is depending on the modules for the routing plane, the forwarding plane, and the I/O, right? And that would be the differentiator among all these within the modular routing plane. When I say how do they differ, we had 3 types of routing plane components, which is the RP1, which is now end OS, end of sale, and then you have the RP2 as well as the RP3. And then looking at the ESP platforms, which is nothing but your forwarding plane, which differs from the ESP5, the ESP10, the ESP20, the ESP40, the ESP100, the 200, the 200X and 100X. Now, when we say these numbers, what do they mean? They mean your bidirectional throughput within the box. And then I talk about the I/O, which is nothing but your SIP10, which is US. It is not supported on Polaris anymore. The SIP40 and your MIP100. The MIP100 will then house 2 things, right? Which is your EPAs, and in your EPAs also you have 3 types. So EPAs are nothing but your Ethernet port adapters, which would be your 1 gig, the 10 gig, and the 100 gig port adapters internally, right? And that's what it houses. Then you come down to your fixed chassis. The fixed chassis starting from 1002, which is EUX. Then your 1X, the 2X, the 2HX, the 1HX, which you know today, right? And they would be a fixed chassis, which when you say that, what you mean is basically they have an integrated routing and the data plane, which mean you don't have a separate module for the RP, you don't have a separate module for any ESP. They all lie within the box itself. Now, the port density and the port combination would then vary. The throughput along these boxes also would vary because the ASICs within the box do vary, right? Next, we come down to the ISR4K family. The ISR4K family, their throughput would change starting all the way up from 2 gig all the way down to 300 meg, right? And the reason why these families have different throughputs is because they want to make sure that every cogs and every requirement of customer is met along those lines. So the same thing applies to the ISR4K families. They differ depending on the type of modules and the type of NIMs, the type of SSDs that they support. Then you have the virtualized form factors, right? Which you know as a CSR 1000V, which is now the last support image that we have is on this V1734A. The replacement modules would be the CAT 8K virtualized form factors. And then you also have the ENCS modules, right? Which is nothing but the ISRVs, which we support. Then you have the ISR1K based families, which would support the Wi-Fi, the LTE, those kind of modules which you might not see in the ASR1K and the ISR4K families. The IO stream does not support SD-WAN. We leave that aside, and then we come to the Viptela family. Most of the Viptela family, the VH100 and VH1000 are out, leaving the VH2K and 5K, but the replacement modules would be the next gen ISR 1000 4G and the 6G, 4G LTE, 6G LTE, which what we have internally called as the Nutella based families, right? The new product lines that have come out on the ASR1K side, which would ultimately replace the 1HX and the 2HX families, what would be the 8500 Green Day and the Ramonas family, which is a part of the 8500 base families, and the 8300 and the 8200 families, but nothing but the Curie based platforms, which would then augment the ISR 4K family to some extent. The other families that are there, which is the Fugazi, which is again how I generally put it is the CSR1K inside a box, right? So that is what it is. Then you have the newer modules, which is the Swizzer, the Nightwatch, the Grimlock, and they nothing but support the different 1G, 2G, and they all supported on the Curie modules. They will be not supported on the ISR original base families. So this is where the product line comes in. SD-WAN is supported on the modular chassis due to Shark Muffin, but not on all the ASR1K families. And your crypto would change accordingly depending on what product line you pick, right? I know licensing is forming a major part now within the product lines, and that would be taken up in later slides where you will see that how the DNA tiers would then impact your throughput within the SD-WAN family. I'll just pause till to now for any questions that are there.
Thanks, Afroz. I think questions are going to come in Q&A. Yeah.
Okay. So at this point, what you need to understand that whichever family you pick, the dependency comes down to for SD-WAN on the crypto modules. In the ASR1K module chassis, the crypto module sits on the forwarding plane. That means your ESP based modules, and the ESP modules would then dictate the crypto that you would you share, right? Then also comes down of the licensing that you have. Anything about 250 Mbps, if the module supports that crypto, you would need an exec license, right? And that would come back into your licensing tier. I think I paused here. I think I have nothing more on the product lines. If any questions, please do post it here.
All right. Thanks, Afroz. And next goes the control plane troubleshooting. I'll pass on to Chindi. Chindi, you can start now. Thank you.
Sure, Guru. Thank you. Just let me share my screen. Good morning, everyone. My name is Chinti Bao. I'm the technical consulting engineer working in SD-WAN team. Today, my colleague Ashish and myself will talk about the SD-WAN control plane troubleshooting part. So here is our agenda. So first, I will.
Cindy, I think we are not able to see your slide, but the mount and the background is what we are seeing now.
Okay. Is it better? Can you see it now?
No, not yet. Probably you'll have to stop and share it again. Maybe
Okay.
give it a try.
Okay, I will stop sharing and share. Guru, can you see my slides now?
I don't think so. Anyone else? Can someone report?
No, Chindi, I think you're check the monitor you're using to share it. Maybe
On my side, it's showing sharing.
we can't see it.
Okay. Just something.
You
We can
want
see
me to
the
share it?
desktop and your cursor moving, but nothing representing.
Are you guys able to see now?
No,
Still
it's
not?
all cursor moving. You want me to try? I can share it and just keep.
Yeah, Shish, maybe you can just quickly see if we can share it.
Yep. Can you guys
Yeah.
make me the presenter?
Yeah,
Okay,
I'm
thank you,
doing it
Ashish.
right away.
Can you guys see the screens now? The slides now?
Yeah, there you
Yeah,
go.
yeah, we can see. Yeah.
Okay, so I will just start it.
Okay, yeah, let's move here. So here is our section agenda. So first, I'll discuss the control connection establishment, and Ashish will cover the troubleshooting part, including basic configuration check and the control connection error legends, and some important troubleshooting and debug commands on VH and CH, and the common control connection errors, and some troubleshooting commands for OMP and OMP graceful restart. Okay. Ashish, can you move to the next one? I think everyone has know some basic theory and architecture of a Cisco SD-WAN solution. So in Cisco SD-WAN, we have 4 planes: orchestration plane, where the vBound works as an orchestrator, and the second one is a management plane, and the vManage is there and manages all the devices. We also have a control plane and the data plane. So on this diagram, we can see we have a blue solid line. This is always on control plane session. Those are control connections. You can see the control connections are established between the controllers and between the edge devices and the controllers. We also have those dot line here. Those are with the those are connections between the edge device and the vBound. So we call those initial control plane session because they are not persistent. So they are set up in the initial stage. Then after all the control connections are set up, those connections will be disconnected. So we mark this as a dot line here. Okay, let's go to next slide. So in common deployment scenarios, we have all the controllers like vBound, VSmart, and vManage. Most of the customers deploy them in the public cloud network. So we have those servers in their VPN 0 network. So the connection is connected to the public internet. And when a VH or CH device comes to the fabric, so we require the device has a network reachability under the VPN 0 as well, so they can talk to those controllers. Ashish, can you move to the next slide? Okay, let's recap some basics here. So control connections are either DTLS or TLS tunnels between the devices and the controllers, or between the controllers. So we know there are no control connections between devices. So control connection, what is the usage of a control connection? It's used as a transport for OMP, and so later on we will talk about more on OMP in another slide. So the control connection is also used for netconf for the vManager to apply templates to all the other devices like VSmarts or edge devices. And it is also used to collect statistics, events, telemetry from the devices. It's also used for management purpose from vManage. So in order to establish control connections, we have 3 steps here. Step 1, we have to define some mandatory parameters and ensure the connectivity. Step 2, we have to whitelist all the devices, controllers, which join to the fabric. So the certificate serial number should be whitelisted in the vManage GUI, and the vManage will push to the vBond. And the device, including controllers and the devices, need to perform the mutual certificates authentication. So it is like bi-directional authentication. Okay, let's go to next slide, please. So step 1, so we need to define some mandatory parameters. So that means the device has to have a valid certificate. And under the system configuration, we have to configure 4 parameters as a minimum. So first one is the system IP, and second is the site ID. Third one is organization name, and the fourth one is a vBond address. So under the VPN 0 configuration, we usually ask at least one device configured as a tunnel interface, and of course you need a valid IP address to be assigned. So there is an exception for vBond. So for vBond, we don't require a tunnel interface on the VPN 0. So the last but not least, the system clock has to be synchronized. That's why we always recommend to use an NTP server over your network. So make sure every device has the same system time. Okay, let's move to step 2. Oh, sorry. So here gives some very minimal configuration for vManage, vBond, and VSmart. So you can see for every controller, we have those 4 parameters configured on the system configuration. So including system IP, site ID, organizing name, and the vBond IP address. And you can see for vManage and VSmart, so under VPN 0, we have a interface configured as tunnel interface, but this is not required for vBond. Let's move to the next one. Okay, step 2, the edge and the controllers whitelist. So this one requires, so for each device in the SD-WAN Fabric, so first step is vManage needed to add them to the vManage GUI. So vManage itself is locally recognized, but for other controllers like vBond and VSmart, administrator has to add them manually, and it will be distributed by vManage to other controllers. Make sure every controller understand that there are those controllers on the network. So for edge devices, so administrator has to whitelist it as well. So we have 2 options here to whitelist it. So option 1, you can click the sync smart account on the vManage device page, and the vManage will automatically pull the edge device list from PNP, and it will be synced with PNP. So another way, you can download the device list serial file number, serial file, and you manually upload it to the vManage. So either way can do the same job. So once the VH list is in vManage, you can push it to all other controllers. It can be done when it's uploaded to vManage, or you can like divide it to 2 steps. Step 1 is just upload the list, and step 2 manually to send to all controllers. Okay, let's move on. So here comes step 3, which is very important for the mutual authentication. So most of these things are covered, already covered in previous session. So I just give a very brief, let's recap it. So in order to authenticate with each other, so certificates need to be exchanged, and then mutual authentication can take place. So for vBond, it needs to validate VSmart, vManage, and VH or CH certificates signed by CA. So the CA can be Cisco CA, can be Semantic CA, or can be your enterprise CA. And vBond validates certificate serial number against authorized whitelist. So that whitelist is from vManage. We talked it in previous slides. So vBond also validates the organization name, which is retrieved from the certificate OU, and it will compare it with the organization name which is configured locally to see if it matches. For VSmart, vManage, and Edge, it needed to validate the vBond certificate signed by CA, and needed to validate the organization name. Similar, it's retrieved from the certificate OU, and it will compare with what is locally configured. Can we move to next one? So for inter-controllers authentication, certificates need to be exchanged, and still we need to do a bidirectional authentication. So VSmart here validates the trustful certificates for other VSmart and vManage certificate signed by CA. It validates certificate serial number against the, what is in the whitelist. It also needed to check the organization name. And for vManage, it's very similar. It needed to validate trust for VSmart certificate serial number, and the organization name. Let's go to the next one. So in this slide, we have the WAN edge device to the controller authentication. Same, we need to exchange certificate and do the mutual authentication. So vSmart and vManage validate edge routers or CH router certificates, certificate serial number, and the organization name. And the router needed to validate the certificate of the controllers like vSmart and vManage, and the organization name. So we use the OTP or token in case it's a software device like a Vedge Cloud or CSR 1000V or C8000V. So they don't have a certificate serial number. Instead, we use token here. Okay, let's move to the next one. So this is the animation for how the router validates the vBond. Actually, can you click the next? Yeah, okay, thank you. So the vBond will send its own certificate with serial number, and the VH will validate the organization name and the serial number. Yeah, the validity of a vBond, which is the serial number, and then we can move to next step. Actually, let's go to the next step. Yeah. Okay, so
sorry.
Okay. Okay, so this one talks about how vBond validates the edge router. So vBond was first sent a 256-bit random value to the router. The router will respond with its own serial number chassis number and the board ID certificate, and it will use its own private key to sign the 250-bit value and send back to the router. Send back to the VBond. When VBond receives those information, it will verify the serial number and the signed 256 random value. So using the certificate. Then the DTLS connection will be set up between the router and the VBond. So this is an example for authentication between the router and the VBond. Okay, let's move on. Okay, so let's have a look at the identity of those routers. So CH router and the VH router, they are a bit different. So for CH router, except for ASR 1002X and software devices, ISR-V and CSR 1000V, each physical CH router is uniquely identified by the chassis ID and the certificate serial number. We call this SUDI certificate. So you can check this long show SD-WAN certificate serial, the command. It will show the certificate serial number. So on the physical router, we have an onboard anti-counterfeit trusted chip. We call it ACT2. So during the manufacturing process, the certificate is already installed, and it also comes with a private key embedded in the ACT2. So the certificate is signed by Cisco root CA because this CH is Cisco routers, and they of course can be trusted by controllers because we know by default all the controllers are installed with Cisco root certificate. So some key use cases. So with this identity, we can verify the integrity of the device, onboarding a new device to the SD-WAN Fabric. We know the ZTP process in the previous session, and we can secure the enrollment within the organizing PKI. So even you use your enterprise CA, they can be onboarded as well. Let's look at the VH router identity in next slide. So kind of similar. So the physical VH router is also uniquely identified by the chassis ID and the certificate serial number. And for each VH devices, they have a serial number which is a 40-byte number, and that is included in the certificate. So on the hardware side, we have an onboard tamper-proof module, TPM module, and the certificate is installed in it during the manufacturing process. So the certificate is signed by ARFnet root CA. So this is different with CH. So CH is signed by Cisco's root CA. But VH can be also trusted by controllers because by default, all the controllers are installed with the ARFnet root certificate as well. So they can use that to decode and to understand this certificate. Okay, so we have two types of security protocol here. In the previous slide, we can see we have DTLS or TLS. So either of them can be used to set up the secure connections. So DTLS runs over UDP and TLS runs over TCP. So that's the difference. And the keep alive for DTLS and TLS is same. The hello interval is 1 second and the hello tolerance is 12 seconds. So we have also two important features which are enabled by default. The first one is called port hopping. So this means when a particular local port for some reason is failed or cannot be used, then the device will automatically hop to the next port. So we have a few ports defined in our document. So they will try one by one if a failure happens. So for port offset, in case in your firewall or you cannot use those ports, you can define the offset. So it will add the offset value to the default predefined the port number. So that's called port offset. So by default, they are enabled, and you can change the configuration if you want. So they are defined in system configuration. Let's move to the next. Okay, let's have a look at the control plane sessions closely. So on this diagram, we can see we have the yellow line. So these are control sessions between controllers, right? Between vManage and vBond, between vManage and VSmart, between two VSmarts, or between vBond and VSmart. So those sessions are DTLS only. So they are permanent connections and can have multiple sessions. And if you look at the gray lines, so those are control sessions between the edge devices and the controllers. So they can be DTLS or TLS. So they are permanent as well. And the OMP can be up on top of those connections. And of course, the vManage use this connection to push the configuration to edge device by netconf. And you also can see a dotted line between the VH and the vBond. So as I said, that's a temporary connection. That's only is used by initial stage. And once all the control sessions are up, so this connection will be disconnected. Okay, we can move to next one. So there is a important protocol called OMP, so Overlay Management Protocol. So OMP is a TCP-based extensible control plane protocol. So it runs between edge devices and VSmart, and also between the different VSmarts. So OMP is running inside TLS or DTLS connections. So let's have a look at what is the usage of OMP. So OMP is used to leverage the address family, and it's used to advertise the reachability for TLOCs, unicast, multicast destinations. So if you have routes, static routes or dynamic routes under your service VPNs, then you can advertise those routes to OMP, and OMP via OMP, all other devices will learn, and the network can be established. So OMP can also advertise service routes. So in a typical use case, we have a firewall sitting on maybe a hub router. So if some customer want the traffic before reaching to another branch site, needed to be inspected by the firewall within the hub router service VPN. You can also publicly advertise the service routes to OMP. So OMP also collect the advertise the BFD stats, which is used for traffic engineering or hierarchical SD-WAN, and also for cloud OnRamp AAS probe stats. So OMP is a bit similar as BGP, so it can use attributes as well. So another usage of OMP is to distribute the IPsec encryption keys. For security purpose, the IPsec encryption keys will be expired after the predefined interval. So the OMP here will be used to distributed IPsec keys as well, and it can distribute the data policy and the app-aware policy from the VSmart to all the devices. Let's move on. Yeah, I think that's the basic theory of the control plane, and I will hand over to my colleague Ashish. He will cover the troubleshooting part for the control plane and OMP. Yeah. Thank you, Ashish. You can take it over.
Thank you, Chindi. Thanks, Chindi. My name is Ashish Gupta, and I'm Chindi's colleague working for SD-WAN APEC time zone. So I will be covering the SD-WAN troubleshooting for the control plane part. So before we start looking into some debugs or the traces, it's good to do some basic verification. So first thing we can check is whether the certificate on the device is a valid one or not. For example, when using enterprise certificate for Cisco SD-WAN devices and controllers, make sure to use root certificates with an RSA key that is at least 2048 bit. Then just verify under the system, we have configured a unique system ID, site ID is correct. Organization name has to be same across all the network devices. VBON FQDN or fully qualified domain name is resolvable. So in case DNS server is not reachable, we can use host to IP entry to resolve VBON FQDN. Next step is to verify under VPN 0. We have configured tunnel interface option. IP address is correct, and we have a corresponding default route to reach the gateway. Also, please make sure that the system clock matches with the controllers. So it should be at least within VBON certificate validity range. We can use show clock command to verify device current time. And in case it's not the correct, we can manually set using the set clock command as well. So these are some of the errors which we can see when the control connections are not getting established. For example, no VM CFG, which means there is no configuration on the vManage for that particular edge device. If the certificate verification is failed, we can use cert VRF failure error. Then in case the serial number is not present, we can use, we will see this CRNT press error. So we will see these frequently seen errors in the upcoming slides as well. So we can use these commands to verify configuration and control connection states on VH, VSmart, and vManage. So first of all, show control local properties. It will display the basic configuration parameters and local properties related to control plane. Using this command, we can verify certificate status, DNS name, VBON address list, and WAN interface list. So in case we are using NAT, it will display both public and private IP address and the ports once control connections are established with VBON. So VBON act as a stun server, and as a result, we can see the public and private IP addresses. Second command, show control connection. It display information about active control plane connections between VH and VBON. So please make sure we have note between VH and VBON we have a transient connection. It doesn't have a permanent connection. So at the time when we are running this command, we might see a control connection between edge and the VBON or not. So when we run this command on VSmart, it displays information about the active control plane connection between a VSmart controller and VBON in the domains. So next is show control connection history. It displays information about control plane connection attempts initiated by the local device. We can verify the error type using this command, and it displays legend of error with brief description. So we can always verify the error code using those legends. So on VH routers and VSmarts, we can run show control valid VSmart to list the serial numbers of the valid VSmart controllers. In case we want to reset the control connections, we can use clear control connection command. We can enable some debugs to verify why control connections are not getting established. We can enable debug vdaemon packets. It controls the debugging of all the vdaemon processes packets, or we can use miscellaneous for the miscellaneous events. Also, we can use debug vdaemon all high for all vdaemon process functions. Some of the important log files which we can see the errors are on the VH are vdebugs, vmessages, the messages, and syslog. We can fetch these files via CLI while going under the vshell, or we can just capture the admin tag and it will be under these directories. So we have equivalent show commands on the CAGs as well. For example, you can use show SD-WAN control local properties or show SD-WAN control connections. Please note down that on VH we have TCP dump utility, whereas on VH we have TCP dump utility, but on CH it's not available. But on CH we have a very important packet tracing utility, and we can use this link to learn more about it. So some of the common errors we see, first of all, is DTLS connection failure. So whenever we see decon fail with the state as connect, normally it means that the packets are not able to reach the VBond. And the most common cause could be the next hop router is not reachable. On the firewall, the ports are blocked. So how can we troubleshoot? So if it is between VH and VBond, for example, you can enable the TCP dumps on either of the sides and see whether the packets leaving from one side are reaching on the other side. Second, you can configure an ACL on and apply on the WAN interface to verify whether the packets are going in and they are going out, and it's we can put a counter against it. Then you can verify if we are using NAT on the firewall, whether it's being correct and the ports are being open for the control connection or not. For example, this is an example which is being used for the TCP dump, which was run on VSmart and on the VH. So on the VSmart, we can see there are certain packets which are of length 1024, which are leaving from the VSmart to the VH. But on the VH, we don't see the packets with the length 1024. So this indicates that there are the packets with higher certain limit. For example, 1024 length, they are being dropped over the ISP. So we can check with the ISP regarding the QoS settings or anything which are dropping the packets for these particular 1024 length. Then the common mistake is organization mismatch, that we have configured a different organization name on the VBond and on the VH. So we will see this kind of error, and we can go under the system configuration and verify we have the correct organization name. Then if we are making some changes, for example, on the color of the TLOC, or we change the system IP, or under any system parameter, we make some changes, we can see the TLOC is disabled. So to resolve it, its simple thing is just bounce that interface or manually clear the control connection, which will refresh the configuration and it will bring up your control connections. Again, if we have configured a duplicate IP, or in the control connection might not come up. So you might see LISFT, which is called listener socket FT error message. This can happen for other reasons as well, such as packet corruption, receiving a reset, mismatching between VH and controller on TLS versus DTLS ports, or if the firewall ports are not open. But the most common cause is duplicate transport IP. Sorry. So another error is this peer timeout error. So this normally happens when the connectivity is not stable and we have a lot of packet loss. So we can see one-way reachability is there. So the troubleshooting method involves is just go under the show control connection detail and you will see the corresponding RX and TX counters. So just verify whether there is no significant discrepancy between these two counters, and all the packets are being reached from one side, leaving one side, are reaching on the other sides. Okay, and in case we have packet drops, maybe check with your ISP that why we are getting too many packet losses. Serial number not present. So if the serial number is not present on the controller for a given device, you will see the control connection failure. So when you troubleshoot such a problem, ensure that correct serial number and device model was configured and provisioned on PNP portal and vManage. It can be verified with show controller valid VSmart or valid VH command. And most of the time, if you go to configuration, certificates, and send to controller or send to vBond button, it will push the serial number edge list from the vBond to the VSmart, and we can verify using above commands whether it's present. In case it is not present, we will see this error ERR underscore bit underscore not verified. So in case the certificates are not valid or the clocks are not synced, then we will see this certificate invalidate error. Okay, so you can manually install the certificate, copy the root certificate from the vManage and install on your edge device. Also verify the clocks are synced using the show clock command. If the clocks are not synced, the device cannot authenticate the certificates. So these are some of the commands which we can use for OMP verification. For example, show OMP peers. It will display information about the OMP pairing session that are active on the local VSmart controller or the VH devices. Show OMP route. It will display information about OMP routes. OMP routes carry information that the Cisco VH device learns from the routing protocols running on its local network, including routes learned from, for example, BGP and OSPF, as well as direct, connected, and static routes. So next we have show OMP services. It displays the services learned from OMP pairing sessions. Then we have show OMP summary. It displays information about the OMP sessions running between VSmart and controllers, VSmart controllers and VH devices. We will see different parameters which will be covered in upcoming slides. Then we have show OMP TLOCs. It displays information learned from the TLOC routes advertised over the OMP session running between the VSmart and the edge devices. We can use clear OMP peer to reset the OMP pairing session with a specific peer. So when you reset a pairing session, the routes to that peer are removed from the OMP route table and they are reinstalled when the peer comes back up. So we can debug OMP packets for debugging of all OMP protocols packets, and we can specify peer address to narrow down. Also, we can use debug OMP events. So this is one of the examples which we can see when we run show OMP summary. It displays the admin state of the OMP session, whether it was up or down. It shows the up time, how long the OMP session was up. It shows the operational status of the OMP session. It also displays how many routes were installed and how many routes were received. Then it shows how many TLOCs were received, for example, and how many TLOCs were installed from its own source, how many TLOCs were sent to the VSmart as well. Next, we can see some more detail about a particular peer. For example, we can use show OMP peers detail. And here we can see for a particular VSmart peer, whether the state is up or down. It's how many routes were installed for that peer, how many routes were received, how many routes sent, and TLOCs installed, TLOCs received, and TLOCs were sent. Then we have OMP graceful restart timer. So in case by default, we have a graceful restart timer of 12 hours. So in that, what happens is that VH or the VSmart will have a cache entry of all the routes, TLOC routes, OMP routes, and service parameters. In case the control connections are lost, it will keep that and those information in its cache for the graceful restart timer period. And once the graceful restart timer expires and the control connections are still not established, these routes are flushed out of the routing table. So we can verify whether the what is configured is using show OMP peer table, show OMP peers detail, sorry, and it will display whether the graceful restart is supported and for how much time it is configured here. Okay. So you can manually change it using timers, graceful restart timer seconds, and we can disable it as well using no OMP graceful restart. So that's all from the control connection troubleshooting part. Thank you.
Thanks, Ashish and Cindy. We can start with the data plane troubleshooting now. Which is Aparna, who's going to
Yeah, I'm going to present first, Guru, but I'm not getting the share option. Okay, yeah,
No,
I got it.
I'm talking about that.
Okay. You're able to see my screen, right?
Yes, yeah, go ahead, Aparna. Yeah, good, thank you.
Okay. Hi team. Now we are going to start with the data plane troubleshooting. Myself and my colleague Vijit Kumar would be covering this topic. So the agenda is going. The agenda is going to be, we'll be covering the data plane basics, basics of the OMP. I think Ashish has covered a bit. I'll be adding some more points related to the data plane troubleshooting part. Debugging, we are going to include both the CH and the VH debugging, and also troubleshooting or basic troubleshooting commands on the VH and the CH. Port handling and NAT, along with port handling with the firewall, and last, the NAT traversal details. So we'll start with the data plane basics. And based on the previous sessions, you would have now got an idea as in what's a TLOC. A TLOC is nothing but a combination of a system IP, color, and encapsulation. The encapsulation can either be an IPsec or a GRE. So all the VHs, once it has the TLOC information and once it has the control connection up with the VSmart, it will advertise this TLOC information to the VSmart via OMP in TLOC routes. It's like an attribute. It will send these TLOC parameters to the VSmart. So once the VSmart receives this route, based on what control policy is configured on the VSmart, it will advertise this TLOC routes to all the other VHs. So this OMP TLOC is very much similar to the BGP next hop in such a way that in order to reach one particular VPN subnet or a VPN route, you'll know which TLOC you should resolve to. And once you have a data plane connection to that data plane connection, wherein the T-logs are the tunnel endpoints, you'll be able to send traffic. So the VSmart would be advertising this T-log routes to the other VHs, and once all the VHs receives this T-log information, it will bring up the data plane tunnels with T-log itself as the endpoint. So by default, this T-log itself can be a public color or a private color. And once we receive the T-log information, or the default behavior is that the VHs will try to bring up the tunnels in a full mesh scenario. That is, in this example, let's say T1 and T3 are internet 1 color, T2, T4 are internet 2 color. By default, T1 will have a tunnel to both T3 and T4. Similarly, T2 will have a tunnel to both T2 and T4. But you can restrict, or you can modify this behavior by using a configuration called restrict. Once you have this restrict keyword, each color will have a BFT session or a data plane tunnel only when the remote color is also same. So it is restricted by the color itself and not by the hierarchy. It's not that public can establish a color, a BFT session with a remote public color. Rather, it's going to be one color, let's say the internet color will be able to establish a connection only to the same color. Similarly, MPLS will form a connection only with the MPLS color. So the use case for this would be, let's say there are a couple of use cases. One thing is very reachability. Let's say the T1 is an internet T-log and T4 is an MPLS T-log. By default, if you don't have a reachability between your MPLS color and an internet color, it will be a waste of resources to try to establish a BFT session between them. So what you can do is, in such cases, you can try to restrict the tunnel formation. And another one useful case would be each platform would have a number of BFT sessions supported. So let's say a VH 1000 supports 250 BFT sessions. So in order to make sure we are running on optimal resources, we shouldn't form a full mesh kind of scenario. Rather, you can go for a hub and spoke topology, wherein all the VHs would forward the traffic to the hub, and from there it will go to the other VHs. So in that scenarios, you can use this restrict keyword. The config as such is very simple. So by default, if you just configure color and let's say MPLS or internet color, it will come up with full mesh scenario. But if you add this restrict keyword, color MPLS restrict, it is going to form BFT sessions only with the remote color same as MPLS. So that's the use of this restrict keyword. And next comes the bidirectional forward detection. Like earlier in couple of slides, you might have noticed that when I mentioned the data plane tunnels will have a BFT formed with the other one. So BFD actually comes in picture between the edges, which has the data plane tunnel. So it runs on both the V edges and the C edges, and it runs inside this IPsec tunnels. As soon as this data plane tunnel is established, the BFD is automatically invoked. There is no way that we can disable the BFD sessions. It's more like a keep alive mechanism to detect failures or failovers more quickly. In addition to detecting whether the tunnel itself is up or down, it can also detect the path liveliness, quality measurements, like what is the loss latency for that particular data tunnel. This information in turn is used in others, like app-aware routing. So that uses this BFT statistics to determine whether the particular tunnel is optimal or not, whether we should be forwarding the packets towards to this tunnel. The parameters used for this BFD is, it has 3 parameters. One is the BFD hello interval. All these hello intervals, one more is the app route polling interval, and another is the multiplier. All these parameters is fully customizable per edge device, and it can be also fine-tuned per color. So all these configurations can be done using these samples. The end device will calculate what is the parameters and what are the quality measurements for a particular data tunnel, and it is used for forwarding as well. And as you know, this data plane tunnels, we have this services that are the interfaces and the sub interfaces are actually mapped to VPNs, and this data plane, the secure IPsec tunnel makes sure that there is a segment connectivity across the fabric. Each VEdge or each edge device maintains a routing table per VPN, and this is for the main control plane separation. And since it's an IPsec tunnel, all the packets are encrypted and we have a headers added to it, whether it is ESP or AH. We'll have to have a field which uniquely determines which VPN packet belongs to, because the VSmart will not send this information to the VEdge routers if that particular service VPN is not present on the remote VEdges. So I'll be receiving a VPN 10 routes only if I have a service VPN 10. The label or the packet which the field which uniquely describes this is the LBL field. This is the label that is used to map the packets into the VPNs for the data plane separation. And here in the slide, we are going to see about the data plane in security encryption. So in traditional networks, what will actually happen is the key exchange is handled by the IKE. That's the Internet Key Exchange. IKE sets up the secure communication between the services to exchange the security parameters, and once the security associations are done, the key exchange actually happens. What happens in the traditional network is, let's say you have n devices, there will be actually n square key exchanges and nearly n-1 keys. So the key exchanges are also messy. The time and resources are also more. The same, in this slide, we'll understand how the same is achieved in this SD-WAN topology. You're able to hear me, right? I just had a power cut. You're still able to hear me, right?
Yeah, Aparna, I can hear you.
Okay, thanks, Ashish. So what happens is each VEdge generates a key called AES key. So once this the VEdges periodically generates this AES key for the data path, and this AES key, it's not per device, it's going to be specifically for per TLOC, and this key information is transmitted to the VSmart in the OMP route package. So in the previous sessions also, you would have seen in OMP we'll transmit the TLOC information, the security keys and stuff. So every VH for one particular TLOC, it will generate a AES key and it will be sending it to the VSmart over the OMP update. Once the VSmart receives this, while it is sending the TLOC information to the remote VHs, it will also be sending the AES key. So this way, my VH A will have the encryption TLOC information as well as the encryption keys for the remote VHs B. That is, it will have the key B1 and B2. And in order to ensure security for this, these keys are periodically regenerated. The default timer is 24 hours. That is, every 24 hours, a new key would be generated and it would be sent, shared over the OMP. And we can be assured that even during this key exchange, there is not going to be a single packet drop. The packets would be properly transmitted. So even though it will be considered secure because the connection between the VEdge and the VSmart itself is a DTLS connection. Further, even though the encryption is a symmetric encryption, that is, a particular packet is being encrypted and decrypted with the same key, it is used in an asymmetric fashion. Meaning, when Vedge A is trying to send packets to Vedge B, it's going to encrypt it in key B1 because the remote color is B1. But when Vedge B is going to send packets to Vedge A, it is again going to use the encryption key that is shared from the VSmart, that is the Vedge A's key 1. So in this way, the number of keys is also reduced, and the security wise, we are doing a periodic regeneration of the keys, and properly the packets are encrypted between one Vedge and the remote Vedge. So this is in terms of data plane security. Next, we'll look into basic troubleshooting. So first thing you'll have to check is the control local properties. So in control local properties output, we'll get to know what is the public and private addresses. So in case it sits behind a NAT, we have the VBON that's acting as a shunt server, and you'll be able to see the public and private address of a TLog in this output. And along with that, you'll be able to understand what's the UDP port over which it is trying to establish the data plane tunnels, the state of the tunnel, what is the color, what are the maximum control connection configurations for this particular interface. So the output is something like this. If you see the show control local properties output, you will see for one interface what's the public color, what's a public port. In case there is no NAT, the public IP and the private IP are going to be the same. And this particular output VS VSS VM, it will show how many like do we have a control connection to the VSmart and vManage, what is the color, what is the state of the tunnel, what is the maximum control connection that is configured, and also it will tell us what are the type of NAT that is being used, and what are the VM connection preference and stuff. So here, while you're, this slide, we can understand that the Vedge, what are the information it will be sending it to the VSmart. One is definitely the reachability information, whether I'm going to, what are the subnets that are reachable from my end, the TLOC information, and one important concept here is the encryption keys, and along with any data policies and app route policies that are being exchanged. So once we have the control property information, we'll every time whenever the edge is trying to form a BFT session, like as we said, the edge device would be forwarding that particular TLOC information to the VSmart. This will not be done unless and until there is a control connection on that particular color. So let's say I have two colors, MPLS and Internet. I'll not be able to send my MPLS TLOC to the VSmart as long as I have the MPLS connection, control connection up on that color. But what happens, there can be a scenario wherein your MPLS network might not be able to reach your controllers, and only your internet TLOC would have a connection to the controllers. In such cases, the BFD sessions will not even come up on your MPLS, and this will impact your data plane redundancy also. So in that case, wherein the reachability itself is not possible, what you can do is there is one command that you can configure, that's the maximum control connection 0. So it's like a workaround for this connectivity issue. In case if you're able to bring the control connections on that color, let's say in some cases the firewall might be blocking the port because of which you're not able to have a control connection. Those things you can fix it without using this command. But in cases wherein truly the reachability itself is not there, you can go for this maximum control connection 0, so that it will know that the control connection is not expected on this interface, and it will try to bring up the BFT sessions, and the TLOC information will also be shared. So I'm going to share 2 or 3 scenarios for troubleshooting scenarios to understand what are the commands to check and how we can approach this problem. So in this diagram, we are going to troubleshoot between BFT sessions between branch 1 VH1 and branch 2 VH2. In some useful commands is going to be show BFT session. This is the first command you should start with whenever you're troubleshooting the data plane. Show BFT history. We'll explain what each commands will look like and what to check in each command. And one important difference between the VH and the CH is that you'll have to add this SD-WAN keyword or for any SD-WAN related outputs. So first, in the working scenario, we can see that branch 1 VH1 has a remote connection or the BFD connection to both the MPLS and the public internet. And the branch 1 is also receiving, let's show OMP TLOCs received. It will show what is the remote system IP, what are the color, what is the encapsulation method, from where I'm receiving this information. This will mostly be the VSmart IP, because it can you can have a number of VSmarts and this will be one of the VSmart IP. It will be what is the status? Have we installed it? Have we rejected it? Have they resolved it? You'll be able to see the status here. So let's consider one scenario wherein the VH1 is not forming a BFD session with a remote public column. If you see the show BFD session, you can filter it for any particular site ID. So here I'm filtering with site ID 20. For site ID 20, I'm having a BFD session, but on the remote TLOC, you can see I don't have a public internet. I just have an MPLS TLOC. So in this kind of situation, the first thing that you'll need to check is whether I'm receiving the public internet TLOC or not. So the command used is show OMP TLOCs received. Here for the system IP 100.2, I don't even see a public internet TLOC. So we know for sure we are not even receiving this TLOC information. Now we can go ahead and check on the branch to VH1 whether I'm advertising or not. So here, if you see, I'm advertising the public internet TLOC, which means the control connections are all up and I'm advertising it properly. So since both the VHs, one side it's not even receiving it and the other end is advertising it, the next point of check would be on the VSmart. On the VSmart, we'll have to check whether I'm receiving the TLOCs or not. And here, when we check the show OMP TLOCs, I'm receiving the public internet, but for some reason, I'm rejecting it. That is why I'm not advertising it to the other VHs. So since the VSmart itself is rejecting it, one possible, the next point of check or one possible reason is a control policy. And here the VSmart is rejecting it. Mostly the problem would be in the control policy ingress direction. So if you check the VSmart running policy, show run policy, control policy, you can see that I'm having a TLOC filtering for 100.2. I'm filtering this public internet. I'm having it in action reject. That is why I'm not forwarding this information to the other TLOC. So once we modify this information, you should be able to have the control connection, or sorry, the BFT sessions up and running. So next scenario, it's the same one. I'm not having a BFD tunnel with the remote color as public internet. This time also I'm checking whether I am receiving the TLOCs or not. I'm not receiving it. So the other one, the next step is whether we are advertising or not. We are not, we are advertising it. And next, we check it on the VSmart. When we check on the VSmart, I can see that I have installed both the MPLS and the public color properly. I'm not rejecting it. So next, in this stage, you can check whether I'm advertising this TLOC information or not. When you check the show OMP TLOCs advertised, here for the public internet column, for site 100.1, I don't in the to peer list, I don't see 100.1, whereas MPLS I'm able to see it. So this situation also proves that there is some kind of filtering happening on the VSmart. Now we can check the policy, and this time it's in the out direction, and it is very specific to the site 20 and for the public, not for all TLOGs, only for the public internet. So some cases this will be essential wherein you don't even want the remote system to know about this TLOG, but in some case wherein it's not expected, you can tweak this control policy. So once you rectify this, you will be able to see that all the BFT sessions are up and running. Let's say I'm receiving all the TLOG information properly, but if you check the show BFT session, it stays in the down state. In that situation, you'll have to start checking the tunnel statistics output. This tunnel statistics will display information about what are the packets that we are sending. If we are sending and receiving correctly, you can continuously give these outputs to understand whether the TX packets and the RX packets are both incrementing. Sometimes only the TX will increment, but the RX will not increment. That will indicate some one-way reachability issue wherein we are able to send packets, but the other end is not receiving it. So this will help to understand whether the issue is within the node itself or some devices in between is blocking those packets. And one more useful command is, in addition to the show tunnel statistics, is the show tunnel statistics BFT. It will show you what are the number of BFD packets that are being sent and received within that data plane tunnel. Here, if you can see, the BFD echo RX packets is 0, but the TX is continuously incrementing. This means that we are not even receiving the packets from the remote end. One more way to isolate, based on this counters itself, we can know that the packets are not being received, but you can also configure an access list to understand how the counters are incremented or not. So the sample configuration looks like this. So from the show BFD session output, you'll know what's the source IP, what's the destination IP that you're going to communicate with. You'll also get to know what's the port number. You can create a two access list, one in the inbound direction, other in the outbound direction, match the IPs properly, and under action accept, you can use this count command. So this will let us know whether, it will count whenever the packets are being hitting this particular sequence 10. You can apply this access list on the interface in the ingress and egress direction, and you can use this output show policy access list counters. And this way we'll know whether the packets from BR1 is going to BR2, whether I'm sending out the packets or not, and whether I'm receiving the packets from the remote end. This way we'll know if the BFT packets are reaching or not. In case if it's not reaching, you'll have to check on the intermediate devices, or on the remote end, you'll have to check whether I'm sending it or not. So in this way, the access list would be helpful. One more is after all this, you're still not able to understand why the packets or the tunnel is not being formed. You can enable this debugs. So the debugs would be slightly different for the VEdge and the CEdge. For the VEdge, you should be enabling the debug FTM BFT. FTM is nothing but the forward traffic manager. And once you enable the debugs, the logs would be present under var log temp log. You can grep for this FTMD output and see what are the reasons for the BFT flap. Why did it flap? Is the timer expired? Do you see any latency? Such information you'll be able to get. And one more useful debug is the TTM events. So in older version, it is TTM BFT. In new version, it's TTM events. And the same log is also seen under temp log. But in CEdge is going to be slightly different. You can do a debug platform software SDWAN FTM BFT or TTM BFT. And in order to look at the logs, you'll have to do show logging process plogd internal, and it will show you the logs are similar, just the way you execute the debugs and retrieve the logs are different. So next is going to be port handling. My colleague Vijit would be taking it over from here.
Hi, good morning everyone. Vijit here. I'm a technical consulting engineer from SDWAN TAC team. So in this section, we will cover port handling and NAT, wherein you have an example like where the devices are behind the NAT, or our vManagers are behind NAT. So how this NAT functions and what are the ports we needed to allow in firewall for your IPsec or the control connections. Next slide, please. So here we will cover what type of NAT we have. This is not specific to SD-WAN. This is universal NAT functionality, so which is full con. We have four type of NATs. One is full con, symmetric, restricted cone, and the last one is port restricted. So we will cover one by one what is full cone. Go to previous slide, please. So in full cone, what happens? So you have a host A which wants to communicate to host B, and this host B is an internet and host A located in an inside network, and you have a NAT device in between. So how Fulcon NAT works? So if you want to communicate to host B, your host A source IP, which is we can say as source A, and then the source port, which is 2001, get translated to source Z and port 3001. And in full con NAT, we don't use any NAT filter. This host A can communicate to any host which is out there in internet. So this is what is full con. So the second is symmetric NAT. So in symmetric NAT, again, the NAT binding will remain the same, but we will place the NAT filter. So in this symmetric NAT, your host A will be communicating to host B on source IP B and the port 90. Okay, so we have a filter enabled here, so that's why we call this as a symmetric NAT. Next slide, please. Okay, now the third one is restricted cone NAT. So in restricted cone NAT, again, the NAT binding will remain the same, where the host A IP address and the port get translated to public IP and the public port. But we have a NAT filter in place where the host A will be able to communicate to host B on all port. Okay, so which is 90 and 91. And the last and the fourth one is port restricted cone NAT, where host they get translated again to the public IP and the public port. But here host they will be able to communicate to all the hosts which is out there in internet on port 90. Okay, so these are the four type of NATs which we use. And in order to work the IPsec to work in SD-WAN Fabric, so these are the recommendation that we need to follow. That if you are if one VH which uses public IP, and second VHS which is in public IP, so we forms the IPsec tunnel. Similarly, on one sided, if you have full cone, and the second you have second side you have a full cone, we forms the IPsec connections. The only restriction what we have is if you have a VH which is behind symmetric NAT, and the second CH which is behind post address restricted, we don't form control connection. Similarly, if both of your devices are behind the symmetric NAT, we don't form control connection. So these are the limitations that you need to keep in mind before placing NAT filter and NAT binding in your firewall or in your NAT device. Next slide, please. Okay, so this is one of the example that travels a dual-sided full cone. So VH1 and VH2, both of these devices are behind full cone. So once VH1 and VH2 forms the control connections with VBond, VBond discovers the post NAT public IP and the communication, and it sends the this public IP and the port details back to the VHS. So here VBond act as a stun server and provide your public IP and the port information back to VH1. So yeah, okay. So VH1 forms the control connection with VSmart. So VH notifies, okay, this is my public IP and the public port number. So once VSmart knows your public and the public port number, VSmart advertise that TLOC information to your other VH devices, and VH devices stores that information in the TLOC parameters, and both of these devices forms a control connection. This is how the NAT traversal work. Next slide, please. Okay. So this is one of the example where you have one side you have full con, the other side you have a symmetric NAT. So once again, VH1 forms the control connection with VBond. VBond passes the public IP information and the port information to respective VHs. Okay, and the VH again forms the connection with VSmart and advertise this information to VSmarts, and followed by VSmart advertise all this TLOC information back to respective VHs. So once VHS stores this information, so if you see here, one-sided we have a full con, the other side we have symmetric NAT. So once the VH1 tries to form a connection with VH2, you will not see the packet coming in because you have a symmetric NAT in place and on VH2 side. Okay, so in symmetric NAT we only allowed connection to VBond. So here what we need is once VH2 gets all the TLOC information from the VSmart, VH2 initiates the IPsec tunneling from VH1. Right here, please. Okay. So this is how it works. So VH2 initiates a connection with VH1. So in your NAT filter device or the firewall device, see this connection and it will allow the bidirectional connections between VH1 and VH2. And this is how your connections forms. So during your, whenever you see any such issue where the IPsec is not forming, first you need to figure out is the devices are behind what NAT. Is it a full con and asymmetric? If it's full con, then we are expecting connections coming from VH2, which is symmetric NAT, then only your IPsec tunnels forms, otherwise your IPsec tunnel will fail. Next slide. Okay, so here we will cover the port handling and the firewall. So as we know that most of our controllers are in cloud, where we assign public IPs, and we have on-prem as well where we can use private IPs. So if your controllers are in cloud and if you want to allow some sort of traffic in your firewall to reach to internet, wherein your VH is in MPLS and using private IP address. So what kind of things we need to keep in mind before placing a firewall rule in your firewall. So here we have few sets of port that we need to allow in our firewall rule to form a control connection and the IPsec tunnel. So the okay, so these are the few ports. In upcoming section I will show you what are the ports we need to form the control connections. So one basic thing you need to keep in mind before placing the firewall rule in place, that if you have multiple devices behind the single NAT device, okay, so each device starts the connection with a base port which is 12346. So if your firewall sees, okay, uh, both of these devices are coming with the same port, okay, and firewall get translated that port to the public and the private, sorry, public IP and the public port, and sends the traffic to your remote controllers. So there are chances that your control connection will fail, okay, because both of these connections are coming from the base port which is 12346. So we need to use a port offset functionality. So what is port offset? So with the port offset you will increase the base port from 12346 to 12347. So the port offset value can be changed from 0 to 19. If I use 18, so we can if I'm using port offset as 18, so my base port will be 123 plus 12346 plus 18. So that will be my base port to form the control connection. So these things you need to keep in mind before placing the firewall rule in place for your control connection and IPsec. And one more thing is port hopping. So we have 5 default port hopping mechanism available in SD-WAN, which is the base port is 12346. If your control connection is failing with 12346, your VHS will try to form a connection on port 12366. And if it fails again on port 12366, then VH will go and try on port 12386 and then 12406 and 12426, and this sequence will keep on running unless the VH forms a connection with your controllers. So whenever you allow a firewall rule, you need to make sure that you allow all these ports 12346, 12366, 12386, 12406, and 12426. Next slide. Okay. So as I mentioned earlier, okay, so once VH tries to connect to your overlay, it start with both base port, which is 12346. Okay, so once the connection fails on 12346, it will go and try on 12366. So all this information you can clearly see in show control local properties. Once the VH forms a connection with VBond, you will clearly see in show control local properties that on what port we are just forming these control connections. So if it is forming control connection on 12406, you will clearly see this on via command, which is show control local properties. Next slide. So this base port functions are slightly different in vManage and vSmart. Okay, so vManage and vSmart running on a virtual VM, where each of these controllers are associated with a virtual CPU, and each of these CPUs are allocated with a individual port number. Okay, so there are possibilities that we are just are forming a control connection on core 6, which is 1 to 946, depending on, because if you have a vManage, okay, vManage, you onboarded 500 devices on your vManage. So it is not necessary that all these 500 devices forms a control connection on core 0, 1, 2, 3, 4, 6. Each of these control connections get redistributed on each of these individual cores. So if you want to allow a firewall rule for this control connection, you need to make sure that you allow all this port, which is 12346, 12446, all these ports which are available there that are associated to each of these core. So all this information you can clearly see with command show control local properties. VBond, we don't use any core. VBond remains using 12346. We don't need any other port for a control connection to form with VBond. It will always be a UDP, which is 12346. For vManage and vSmart, either it can be DTLS or TLS. If it is DTLS, the port starts with 1. If it is TLS, all of this port number starts with 2. So 2 in upcoming section will show you how this TLS ports look like. Next slide. Okay, so this is one of the examples how the firewall ports needs to be deployed for your control connection to be formed from VH to your controllers. Okay, so we need to make sure that all these ports are open on your firewall for your vManage as well as for your vBond, and along with this, VH ports. So you need to make sure that all of these ports are open in your firewall. Then only your control connection forms. So there are cases where customer allowed only 1, 2, 3, 4, 6 by any reason the control connection fails on 1, 2, 3, 4, 6, and VH goes and tries port 1, 2, 3, 6, 6, and it fails because we don't have a firewall rule available for 1, 2, 3, 6, 6. So we need to make sure that we allow all this port in your firewall rule to form control connections and BFD. Next slide. Okay, so this is what I was talking about, a TLS connection. If your vManage and vSmart are using TLS connection, so you need to make sure that you allow this port, and the port starts with 2, which is 23456, 23556. Each of these ports are allocated to your each individual course. VH remains the same. We don't change any connection as port number on VHS. So it will be the firewall which will be changing your port number, right? So yeah. Next slide. Yeah. So NAT travels a detail. So here we will cover how VHA forming a PFD session with VHP. Okay, this is one of the example where VHA is behind a full con NAT device and VHP is behind one of the symmetric NAT device. So in order to form a successful IPsec tunnel, So each of these VHs should know what is the public IP and the public port of peer device. So once VHA forms a connection with VBond sends the public and the public port information back to that VH, and then VHA advertise that information back to VSmart, and that's how VSmart knows, okay, this is the public IP and the public port for this respective VHS. Next slide. Okay, side arrow, please. Okay. Okay, so this is uh, again, this is the same example where okay, there's nothing to cover here. Next slide. Okay, so this is how the OMP information looks like. Okay, so if you go and check the OMP T-log information, you will see all these attributes are associated to that respective T-logs, where you will be able to see what is my public IP, public port, private IP, and private ports. So there are use cases where your VHS are behind the NAT devices, and VHS are trying to form a BFD session over private IP. So first thing you need to check is go and check in VSmart. Are the VSmart are receiving the public IP and the port information from VHS or not? So from there we need to start how to troubleshoot the BFD issues where VHS are trying to form IPsec tunnel over private IP address. So it is VSmart who is responsible to advertise all this information to peer VH devices. Next slide, please. Okay, so this is how the TLOG get advertised. So VHA here in this example, we can see that VHA is using IP address as A, and the port is 12346, and ISP box translate this private IP and the private port to public IP as Z and public port as 3001. VSmart advertise this information back to VHB. Okay, and VHB stores this information. Okay, for if you go and check the show MPT log information, you will see that VH is holding information for VHA as public IP as Z and 3001. Next slide. Similarly, VHP forms a control connection with VSmart. VSmart advertises public IP and the public port details to VHA, and VHA stores that information in its OMPT log table. Next slide. So this is how the we can run this command show OMP log received. We will see what is peer log IP and the peer public IP and the peer private public port and the private port. All this information we can clearly see if we run this command show OMP logs received. So first you need to run in VSmart. You need to make sure that VSmarts are receiving this information correctly from respective VHS. And second, on VHS to see if we are receiving this information from VSmart correctly or not. Next slide. Okay. So once both of these devices passes informations, so they can go and try to form IPsec tunnel. So here you can see that left hand side we have full cone and the right hand side we have symmetric, right? So if VH1 tries to form a IPsec tunnel to VH2, so mostly it will fail because we have a symmetric NAT in place on ISP1 box which is connected to VH2. So here we want VH2 to form a connection with VH1. So once the VH2 tries to form a next slide, yeah, here your IPsec will fail. So VH2 starts initiating IPsec connection with VH1, and once VH1 gets that information, once the ISP1 box which is connected to VH1 forward the traffic, it will allow reverse traffic as well. So your IPsec will form. Next slide. So yeah, so this is one of the basic command that you need to run to figure out, okay, so what type of NAT you are using. So we have in VH terminology, we are using 3 type of NAT, which is E. We can run this command to control local properties WAN interface list. So we can see 3 type of NATs here, which is E. First indicates endpoint independent mapping, and the second one is A, which is which indicates address port dependent mapping, and the last one is N, indicates not learned. So there are scenario that where the control connection formed, but we are just not learning the NAT type, and it indicates not learned, and you can see that NAT types as N. So there are chances that your IPsec will fail if any of our devices which is behind your NAT device, your IPsec will fail. So we need to figure out why it is failing and why we are just learning. We are just not learning the NAT type. So these are the few of the basic troubleshooting practices that we need to follow to figure out why the IPsec tunnels are failing, why the control connections are failing. So these are few useful commands that you can refer. Useful link basically. So the first one is specific to VHs. The second one again VHs. So we have a separate documentation for CH, which we will paste on this particular PPT and we will send over. And the last one is for firewall ports for VPLI deployments. You need to refer this document carefully to figure out what type of ports you need to allow in your firewall in order to successfully deploy SD-WAN devices in your overlay. Okay, so these are the few links that you need to refer. Yeah, thank you everyone.
Thanks, Vijit and Aparna. Thank you so much, everyone, joining us today. I think we are done with today's session. So most likely we will again start tomorrow morning. Thank you so much. We will join again tomorrow morning. Thank you.